so-called apogee. This keep on increasing like this, okay? This keep on increasing like this, and the orbital period is also keep on increasing. This is what happens. Each one of the day when you do the maneuver, this happens there. To do that, what we have done is, this is talks about pre-plan. I told the schedule the plan, not only schedule plan, how will the operation to plan. This is as plan, okay? And as plan, and now once orbit comes, each one of the orbit comes, we see what the orbit has achieved, and accordingly find through the number. Again, this is also planned, but planned means using the exact orbit. Because when we are going around there, also we will have to track using the tracking system, we will have to judge what is the orbit of the real orbit of the satellite. From that, one go to next orbit. How much you have to do, that you are doing the other way. Then you apply that values here. Then this is what you apply, and you are asking the system to do the function, and if the realized rate is something like this. It is realized here, then again it is accommodated here. That is, each one of the maneuvers, what is planned originally before the launch, and what we have done as per the orbit, and what is the one we are uplinking. It is small difference we are uplinking, because this is automatically system should take place. Okay. Now what is happening is, when the maneuver is taking place, we are supposed to give a velocity of somewhere around 201.893 meters per second you have to give. But you give the value such that end of that value should stop. But what is happening is, the software point that you look at here, it looks for accelerometer. The accelerometer starts with what is the incremental velocity has come, it sees. Minimum 3 samples you have to see. Software you have to look for, because software errors should not create a problem. 3 samples you are seeing, then you are terminating. 3 samples, what is happening is about this. When you are trying to see, there is a possibility of the timing other point of view. It will spill over to slightly more. So you account for that, it's slightly less here. Just that you are trying to get what you are looking for. That's what being done here. And accordingly, you look at here what you wanted, this much you wanted, and this much you really slightly more over performance really happened. You originally plan, and real orbit what you plan, and really what you achieve. It starts about here. When we are talking about here, that translates into how much time thrust has fired. Okay, this is already accounted here. There is a 440 Newton engine, the smaller rocket of that it fires during the particular time period, and how much time that fire, okay, and how much delta we realize, and what does the propellant spend, because we are spending the propellant. We have to keep account of that propellant also. Okay, you have to go to the Mars using the same propellant. So we have to keep account of that. And this talks about that. How much each one on the stage, how much propellant we have spent. Nearly 531 kg we have spent there. What we loaded is 850. That means nearly we have 320 kg of propellant. Still it is left there. Now having done that, now this is what the last, like whatever I told. Okay, this is last elliptical arc around the earth. And this, when we are coming here, we are giving a final maneuver around that. From that, Mars injection. Okay, from there it is, as I told here, towards Mars is going, but around the sun. But this particular one is done here, and the orbit has been taken off like that. And now that comes another way. Okay, now this is engineering. This is, as I told here, engineering interdisciplinary is the thing here. Okay, when we talking about here schedule, we talk about the power, we talk about the mass, we talk about the money, everything. But still, longer the targets, another engineering aspect is, longer the targets, finer the tolerance to the errors. Okay, we are going to the 400 km orbit, 800 km orbit, 3600 km orbit, 4 lakh km orbit. Now we are going for a target which is nearly 200 million km away. Longer if you go, the tolerance what you there for the errors is very, very minimal. Okay, because what you do here, it reflects there, much time later. So if you make an error, for example, you told about 200 meters per second, but there is an error limit. Beyond that, if you go, it integrates over the 9 months, and when we go there, near the orbit, we will much away. You will be amazed to see what is the number we are talking about here. Okay, this you look at here. Typically, and let's like I tell you, if you make an error of 30 millimeters per second per velocity, incremental velocity, you are bound to hit the Mars. Okay, that means you are bound to fail. That translates one of the 4 causes of failure is going to happen. That means you cannot afford to have errors. The maneuvers what you are doing here, you cannot do the maneuvers left and right. You have to ensure the maneuvers what you targeted are within the error limits of within few millimeters per second in velocity. We are talking about incremental velocity of few kilometers. What we are talking about is Mars is going for 11 km per second, velocity is going, and then we are talking about that. But you cannot afford to have an error of few millimeter per second. In case that is there, you are supposed to correct it. That's what this manual, then whatever, 11th December 2013, that few meters per second velocity we are correcting it there. Now you look at here.